Welcome to the Astronomy 95 channel, and this is the NASA's Top Stories Episode 3. In this episode, we will talk about superheavy neutron stars, the enduring stellar lifecycle in 30 Doradus, dig out buried black holes with NASA's Chandra, star formation in clusters dusty ribbons, and more other top stories of NASA. Hundreds of black holes previously hidden, or buried, have been found using NASA's Chandra X-ray Observatory. The black holes in this new study are the supermassive variety that contain millions or even billions of times the mass of the Sun. While astronomers think that almost all large galaxies harbor giant black holes in their centers, only some of the black holes will be actively pulling in material that produces radiation, and some will be buried underneath dust and gas. A survey has revealed hundreds of previously unidentified black holes using data from the Chandra Source Catalog and the Sloan Digitized Sky Survey. Researchers compared the X-ray and optical data for a class of objects known as SMACS to reveal about 400 supermassive black holes. These graphics show these SMACS in X-rays from Chandra and optical light from Sloan Digitized Sky Survey. Further study revealed that about half of these SMACS represent a population of previously hidden black holes. X-rays are particularly useful to search for rapidly growing black holes because material swirling around them is superheated to millions of degrees and glows strongly in X-ray wavelengths. A thick cocoon of gas and dust surrounding a black hole will block most or all the light at optical wavelengths. After studying the amount of X-rays detected at different energies for each source, the team concluded that about half the SMACS candidates involve X-ray sources that are buried under thick gas because relatively small amounts of low-energy X-rays were detected. These X-ray sources are so bright that almost all of them must be from material surrounding rapidly growing supermassive black holes. Data from NASA's Wide Field Infrared Survey Explorer provides additional evidence that about half of the SMACS are buried, growing supermassive black holes. These black holes range in distances between 550 million and 7.8 billion light-years from Earth. About 100 of the X-ray sources may not be single points of X-ray sources, but instead appear spread out. The remaining 30% may contain some supermassive black holes located in galaxies where the optical signals from the supermassive black holes are diluted by relatively bright light from stars. These are termed tidal disruption events. But the wording belies the complex, raw violence of a black hole encounter. There is a balance between the black hole's gravity pulling in star stuff and radiation blowing material out. In other words, black holes are messy eaters. Astronomers are using Hubble to find out the details of what happens when a wayward star plunges into the gravitational abyss. Hubble can't photograph the 2022 DSB tidal events mayhem up close, since the munched-up star is nearly 300 million light-years away at the core of the galaxy ESO 583G004. But astronomers used Hubble's powerful ultraviolet sensitivity to study the light from the shredded star, which include hydrogen, carbon, and more. The spectroscopy provides forensic clues to the black hole homicide. About 100 tidal disruption events around black holes have been detected by astronomers using various telescopes. NASA recently reported that several of its high-energy space observatories spotted another black hole tidal disruption event on March 1, 2021, and it happened in another galaxy. Unlike Hubble observations, data was collected in X-ray light from an extremely hot corona around the black hole that formed after the star was already torn apart. For any given galaxy with a quiescent supermassive black hole at the center, it's estimated that the stellar shredding happens only a few times in every 100,000 years. This 2022 DSB stellar snacking event was first caught on March 1, 2022 by the All-Sky Automated Survey for Supernovae, a network of ground-based telescopes that surveys the extragalactic sky roughly once a week for violent, variable, and transient events that are shaping our universe. This energetic collision was close enough to Earth and bright enough for the Hubble astronomers to do ultraviolet spectroscopy over a longer than normal period of time. The Hubble spectroscopic data are interpreted as coming from a very bright, hot, donut-shaped area of gas that was once the star. This area, known as a torus, is the size of the solar system and is swirling around a black hole in the middle. The solar wind was first proposed in the late 1950s by the visionary scientist Eugene Parker, namesake of the Parker Solar Probe. Parker's theory eventually became a leading candidate to explain the heating and acceleration of the solar wind. Continued observations from Parker's solar probe and other instruments such as NASA's polarimeter to unify the corona and heliosphere, and the Daniel K. Inouye Solar Telescope, will help scientists confirm whether jetlets are the main source of solar wind. Scientists with NASA's Parker Solar Probe mission have uncovered significant new clues about the origins of the solar wind, a continual stream of charged particles released from the sun that fills the solar system. Observations from multiple space and ground-based observatories show the solar wind could be largely fueled by small-scale jets, or jetlets, at the base of the corona, the sun's upper atmosphere. Understanding the solar wind is fundamental to our understanding of our solar system and others throughout the universe and is the primary science goal of the Parker Solar Probe mission. Made of electrons, protons, and heavier ions, the solar wind courses through the solar system at roughly 1 million miles per hour. Over time, the solar wind, and stellar winds in other solar systems, can also affect the composition and evolution of planetary atmospheres, even influencing planets' habitability. Scientists have therefore been looking for a steady source at the sun that could continually power the solar wind. Though each jetlet is relatively small, just a few hundred miles long, their collective energy and mass could be enough to create the solar wind. In the solar corona, reconnection creates these short-lived jets of plasma that pass energy and material into the upper corona, which escape across the solar system as the solar wind. To study the jetlets and magnetic fields, scientists primarily used observations from the Solar Dynamics Observatory and the Geostationary Operational Environmental Satellite R-Series Solar Ultraviolet Imager instrument, as well as high-resolution magnetic field data from the Good Solar Telescope at the Big Bear Solar Observatory in California. The whole study was driven by a phenomenon first observed by Parker's solar probe called switchbacks, magnetic zigzag structures in the solar wind. The scientists calculated that the energy and mass produced by the jetlets could provide most, if not all, of the amount of energy and mass seen in the solar wind. Astronomers studying archival observations of powerful explosions called short gamma-ray bursts have detected light patterns indicating the brief existence of a superheavy neutron star shortly before it collapsed into a black hole. This fleeting, massive object likely formed from the collision of two neutron stars. A neutron star forms when the core of a massive star runs out of fuel and collapses. This produces a shock wave that blows away the rest of the star in a supernova explosion. Neutron stars typically pack more mass than our Sun into a ball about the size of a city, but above a certain mass, they must collapse into black holes. Both the Compton data and computer simulations revealed mega-neutron stars tipping the scales by 20% more than the most massive, precisely measured neutron star known, dubbed J07406620, which weighs in at nearly 2.1 times the Sun's mass. Superheavy neutron stars also have nearly twice the size of a typical neutron star, or about twice the length of Manhattan Island. The mega-neutron stars spin nearly 78,000 times a minute, almost twice the speed of J1748-2446 AD, the fastest pulsar on record. Short gamma-ray bursts typically shine for less than 2 seconds yet unleash energy comparable to what's released by all the stars in our galaxy over 1 year. Merging neutron stars also produce gravitational waves, ripples in spacetime that can be detected by a growing number of ground-based observatories. Computer simulations of these mergers show that gravitational waves exhibit a sudden jump in frequency exceeding 1000 Hz as the neutron stars coalesce. Both the gamma-ray and gravitational wave quasiperiodic oscillations originate in the maelstrom of swirling matter as the two neutron stars coalesce. While no gamma-ray QPOs materialized in the Swift and Fermi bursts, two short gamma-ray bursts recorded by Compton's Burst and Transient Source Experiment on July 11, 1991, and November 1, 1993, fit the bill. The larger area of the Burst and Transient Source Experiment instrument gave it the upper hand in finding these faint patterns, the telltale flickering that revealed the presence of mega-neutron stars. By the 2030s, gravitational wave detectors will be sensitive to kilohertz frequencies, providing new insights into the short lives of supersized neutron stars. Using data from NASA's Transiting Exoplanet Survey satellite, scientists have identified an Earth-size world, called TOI 700e, orbiting within the habitable zone of its star, the range of distances where liquid water could occur on a planet's surface. The world is 95% Earth-size and likely rocky. Astronomers previously discovered 3 planets in this system, called TOI 700b, C, and D. A planet D also orbits in the habitable zone. But scientists needed an additional year of TESS observations to discover TOI 700e. TOI 700 is a small, cool M-dwarf star located around 100 light-years away in the southern constellation Doradus. In 2020, Gilbert and others announced the discovery of the Earth-size, habitable zone planet D, which is on a 37-day orbit, along with 2 other worlds. The innermost planet, TOI 700b, is about 90% Earth-size and orbits the star every 10 days. TOI 700c is over 2.5 times bigger than Earth and completes an orbit every 16 days. The planets are probably tidally locked, which means they spin only once per orbit such that one side always faces the star, just as one side of the Moon is always turned toward Earth. TESS monitors large swaths of the sky, called sectors, for approximately 27 days at a time. These long stares allow the satellite to track changes in stellar brightness caused by a planet crossing in front of its star from our perspective, an event called a transit. The mission used this strategy to observe the southern sky starting in 2018, before turning to the northern sky. In 2020, it returned to the southern sky for additional observations. The extra year of data allowed the team to refine the original planet sizes, which are about 10% smaller than initial calculations. TOI 700e, which may also be tidally locked, takes 28 days to orbit its star, placing planet E between planets C and D in the so-called optimistic habitable zone. Scientists define the optimistic habitable zone as the range of distances from a star where liquid surface water could be present at some point in a planet's history. This area extends to either side of the conservative habitable zone, the range where researchers hypothesize liquid water could exist over most of the planet's lifetime. TOI 700d orbits in this region. Researchers confirmed an exoplanet, a planet that orbits another star, using NASA's James Webb Space Telescope for the first time. Formally classified as LHS 475b, the planet is almost exactly the same size as our own, clocking in at 99% of Earth's diameter. The research team is led by Kevin Stevenson and Jacob Lustig-Jaeger, both of the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland. The team chose to observe this target with Webb after carefully reviewing targets of interest from NASA's Transiting Exoplanet Survey satellite, which hinted at the planet's existence. Webb's near-infrared spectrograph captured the planet easily and clearly with only 2 transit observations. A flat line in a transmission spectrum, like this one, can be exciting. It can tell us a lot about the planet. Researchers used NASA's James Webb Space Telescope's near-infrared spectrograph to observe exoplanet LHS 475b on August 31, 2022. As this spectrum shows, Webb did not observe a detectable quantity of any element or molecule. The data are consistent with a featureless spectrum representative of a planet that has no atmosphere. The purple line represents a pure carbon dioxide atmosphere and is indistinguishable from a flat line at the current level of precision. The green line represents a pure methane atmosphere, which is not favored since if methane were present, it would be expected to block more starlight at 3.3 microns. Among all operating telescopes, only Webb is capable of characterizing the atmospheres of Earth-sized exoplanets. The team attempted to assess what is in the planet's atmosphere by analyzing its transmission spectrum. Although the data shows that this is an Earth-sized terrestrial planet, they do not yet know if it has an atmosphere. The researchers also confirmed that the planet completes an orbit in just 2 days, information that was almost instantaneously revealed by Webb's precise light curve. Although LHS 475b is closer to its star than any planet in our solar system, its red dwarf star is less than half the temperature of the Sun, so the researchers project it still could have an atmosphere. A light curve from NASA's James Webb Space Telescope's near-infrared spectrograph shows the change in brightness from the LHS 475 star system over time as the planet transited the star on August 31, 2022. LHS 475b is a rocky, Earth-sized exoplanet that orbits a red dwarf star roughly 41 light-years away, in the constellation Octans. The planet is extremely close to its star, completing one orbit in 2 Earth days. The planet's conformation was made possible by Webb's data. A new analysis of distant galaxies imaged by NASA's James Webb Space Telescope shows that they are extremely young and share some remarkable similarities to green peas, a rare class of small galaxies in our cosmic backyard. A trio of faint objects captured in the James Webb Space Telescope's deep image of the galaxy cluster SMACS 0723 exhibit properties remarkably similar to rare, small galaxies called green peas found much closer to home. The cluster's mass makes it a gravitational lens, which both magnifies and distorts the appearance of background galaxies. The farthest P, at left, contains just 2% the oxygen abundance of a galaxy like our own and might be the most chemically primitive galaxy yet identified. Green pea galaxies were discovered and named in 2009 by volunteers taking part in Galaxy Zoo, a project where citizen scientists help classify galaxies in images, starting with those from the Sloan Digital Sky Survey. Peas stood out as small, round, unresolved dots with a distinctly green shade, a consequence of both the colors assigned to different filters in the survey's composite images and a property of the galaxies themselves. Green pea galaxy colors are unusual because a sizable fraction of their light comes from brightly glowing gas clouds. In July 2022, NASA and its partners in the Webb mission released the deepest and sharpest infrared image of the distant universe yet seen, capturing thousands of galaxies in and behind a cluster known as SMACS 0723. Among the faintest galaxies behind the cluster were a trio of compact infrared objects that looked like they could be distant relatives of green peas. The most distant of these 3 galaxies was magnified by about 10 times, providing a significant assist from nature on top of the telescope's unprecedented capabilities. Webb did more than image the cluster. Its near-infrared spectrograph instrument also captured the spectra of selected galaxies in the scene. The James Webb Space Telescope's near-infrared spectrograph captured the chemical fingerprints of selected galaxies behind SMACS 0723, including 3 faint, distant objects. When corrected for the wavelength stretch caused by the expansion of space over billions of years, the spectra of these galaxies exhibit features emitted by oxygen, hydrogen, and neon that show a stunning resemblance to those seen from so-called green pea galaxies found nearby. The Webb observations made it possible to measure the amount of oxygen in these cosmic dawn galaxies for the first time. 2 of the Webb galaxies contain oxygen at about 20% of the level in our Milky Way. NGC 346, one of the most dynamic star-forming regions in nearby galaxies, is full of mystery. Now, it is less mysterious with new findings from NASA's James Webb Space Telescope. NCG 346 is located in the Small Magellanic Cloud, a dwarf galaxy close to our Milky Way. The Small Magellanic Cloud contains lower concentrations of elements heavier than hydrogen or helium, which astronomers call metals, compared to the Milky Way. Since dust grains in space are composed mostly of metals, scientists expected there would be low amounts of dust, and that it would be hard to detect. New data from Webb reveals the opposite. NGC 346, shown here in this image from NASA's James Webb Space Telescope near-infrared camera, is a dynamic star cluster within a nebula 200,000 light-years away. Webb reveals the presence of many more building blocks than previously expected, not only for stars, but also planets. The effect of this is seen in the various ridges throughout, which are created as the light of these young stars break down the dense clouds. In this image, blue was assigned to the wavelength of 2.0 microns, green was assigned to 2.77 microns, orange was assigned to 3.35 microns, and red was assigned to 4.44 microns. Astronomers probed this region because the conditions and amount of metals within the Small Magellanic Cloud resemble those seen in galaxies billions of years ago, during an era in the universe known as cosmic noon, when star formation was at its peak. Some 2 to 3 billion years after the Big Bang, galaxies were forming stars at a furious rate. The fireworks of star formation happening then still shape the galaxies we see around us today. By observing protostars still in the process of forming, researchers can learn if the star formation process in the SMC is different from what we observe in our own Milky Way. Previous infrared studies of NGC 346 have focused on protostars heavier than about 5 to 8 times the mass of our Sun. As stars form, they gather gas and dust, which can look like ribbons in Webb imagery, from the surrounding molecular cloud. The material collects into an accretion disk that feeds the central protostar. Astronomers have detected gas around protostars within NGC 346, but Webb's near-infrared observations mark the first time they have also detected dust in these disks. The largest and brightest region of star formation in the local group of galaxies, including the Milky Way, is called 30 Doradus. Located in the Large Magellanic Cloud, a small neighbor galaxy to the Milky Way, 30 Doradus has long been studied by astronomers who want to better understand how stars like the Sun are born and evolve. NASA's Chandra X-ray Observatory has frequently looked at 30 Doradus over the lifetime of the mission, often under the direction of Dr. Lisa Townsley, who passed away in the summer of 2022. These data will continue to be collected and analyzed, providing opportunities for scientists both now and in the future to learn more about star formation and its related processes. This new composite image combines the X-ray data from Chandra observations of 30 Doradus with an infrared image from NASA's James Webb Space Telescope that was released in the fall of 2022. The X-rays reveal gas that has been heated to millions of degrees by shock waves similar to sonic booms from airplanes generated by the winds from massive stars. The Chandra data also identify the remains of supernova explosions, which will ultimately send important elements such as oxygen and carbon into space, where they will become part of the next generation of stars. The infrared data from NASA's Webb shows spectacular canvases of cooler gas that provide the raw ingredients for future stars. James Webb's view also reveals protostars, that is, stars in their infancy, just igniting their stellar engines. The chemical composition of 30 Doradus is different from most of the nebulas found in the Milky Way. Instead, it represents the conditions in our galaxy that existed several billion years ago, when stars were forming at a much faster pace than astronomers see today. This, combined with its relative proximity and brightness, means that 30 Doradus provides scientists with an opportunity to learn more about how stars formed in our galaxy in the distant past.